The question about the exact nature and dimensions of the universe is as old as star research itself. A look at history shows that the terrestrial picture of our galactic home has already undergone some drastic changes. Whereas people in the past assumed that the universe was a comparatively small entity with the Earth at its center, the gigantic expanse of space is now described by many modern experts as infinite. Today, we would like to take a closer look at this galactic infinity and compare it with the common theories of experts. We'll illuminate both the spatial and the existential infinity of our galactic home. Does the universe have something like a clearly delineated edge? And will the cosmos one day meet a final fate? Together with you, we are looking for answers. Want to join us on our journey to the greatest mysteries of the universe? Then don't forget to subscribe and activate the bell to stay up to date from now on. Feel free to show us with a thumbs up that you like the topics of our videos. Does the universe have an edge? By now, we know that the universe is constantly expanding. In fact, in the 1990s, it became known that this galactic expansion is even happening much faster than scientists had previously predicted. In view of this fact, a central question arises. If the universe is expanding, into what space is it growing? Or to put it another way, what is beyond the universe? This question implies the assumption that the universe has something like a spatial edge. At this point, however, it begins to get a little complicated because, in fact, experts still do not agree whether such a cosmic abyss really exists. In order to visualize this exciting topic, we can imagine the universe as a large building. For the sake of simplicity, is there a kind of edge within this building, like a window, over which we can look in order to see the areas beyond? The answer to this question is probably not. One reason for this is the so-called cosmological principle. This basic assumption of scientific cosmology states that the universe is homogeneous and isotropic. In detail, this means that the universe always presents itself to the observer in the same way, regardless of his point of view and direction of observation. The cosmological principle is based not least on the assumption that the same physical laws prevail in every part of space. Although the different regions of the universe show some differences in detail in their respective constellations of celestial bodies, in the overall context, no place in the universe is fundamentally different in structure than elsewhere. Consequently, there is no edge in the cosmos, nowhere we could go to see what is outside the universe. The balloon analogy. A metaphor often used to visualize this borderless universe is that of a small insect deposited on the surface of a balloon. This little creepy crawly can run there endlessly in any direction without ever encountering a clearly discernible edge. Even though the surface of the balloon is known not to be an infinite structure, from the insect's perspective, however, it has neither a boundary nor a recognizable center. But how is it possible within this balloon analogy that the structure, or in other words, the universe, constantly expands if it does not have an edge itself? If we pumped more and more air into the balloon, the insect would notice with time that the things on the balloon surface moved further and further away from each other. At the same time, the speed with which the corresponding objects drifted apart would always remain the same. At this point, however, the balloon analogy reaches its limits. While the balloon expands into a three-dimensional space, this scheme cannot be applied to the universe. By scientific definition, there is no outside for the universe. Therefore, the universe does not expand into an external space, but it's the contained space itself which grows continuously. While many researchers rack their brains in view of this complex topic, Stephen Hawking dismissed the question about what lies beyond the universe as nonsensical from the outset, based on the fact that the universe formed out of nothing and contains everything that exists. One might as well ask what lies further north than the North Pole. Exactly how the expansion of the universe occurs has always been a subject of debate in scientific research. For example, experts still argue about whether the universe is infinite in space at all. Theoretically, the universe could also practically wrap around itself in a higher dimension, roughly in the same way that the two-dimensional surface of a sphere spans around itself in 3 dimensions. To verify whether the aforementioned balloon metaphor is consistent with the real characteristics of the universe, experts are looking for repeating points in the sky, analogous to the assumption that the insect on the balloon could run in one and the same direction until it finally returns to its starting point. Such a discovery in the firmament would be a strong indication that the universe is indeed curved in this way. The end of the universe. Although the universe is commonly referred to as an infinite entity, many experts agree that this designation refers only to the spatial manifestations of the universe. Consequently, the universe could one day arrive at the final chapter of its lifespan and eventually reach its galactic end. As to how the end of our cosmic home will proceed exactly, different theories exist. A widespread thesis is called the Big Rip and refers to the steadily increasing expansion rate of the universe. Ultimately, the expansion processes of the cosmos, fueled by a special form of dark energy, would culminate in a so-called singular event. As a reminder, within astronomy, singularities are those places where gravity is so strong that the curvature of space-time is colloquially infinite. Generally, the experts agree that our universe originated in the course of the Big Bang from such a singularity. Transferred in reverse to the Big Rip, this process would mean that the universe is torn apart from the largest to the smallest structures. First, the large galaxy clusters would be torn apart, then galaxies, individual celestial bodies, atoms, and ultimately, elementary particles. Big Crunch. As mentioned earlier, however, the Big Rip model is not the only theory used to predict the end of the universe. While in this variant, the universe ultimately falls victim to its own unchecked increasing expansion rate, the Big Crunch scenario is based on the influence of the gravitational force. Under the influence of this force, the universe would visibly collapse before it finally undergoes a kind of reverse Big Bang and finally disappears completely. Based on the assumption that dark energy would diminish over time, the effects of gravity would exceed the effects of this force in a few trillion years. Once this occurs, the expansion of the universe would come to a complete halt, effectively reversing itself. Instead of growing steadily, natural processes would henceforth drive an accelerated contraction of the universe. As a result, the temperature would also continue to increase. About 100,000 years before the final Big Crunch, the cosmic microwave background radiation would eventually be hotter than the surface of stars. Immediately before the end of the universe, the intense radiation would explode atomic nuclei, transforming them into gigantic black holes. These supermassive gravity monsters would then merge with one another and unite into a single black megahole. This monstrous structure would eventually contain all existing matter and finally swallow itself at the very last moment before the Big Crunch. According to the opinion of some scientists, this process would not necessarily mean the irrevocable end of the universe. Furthermore, it's conceivable that such a Big Crunch might be followed by another Big Bang and a new universe being born. Big Freeze. As the name suggests, the so-called Big Freeze predicts a literal frosty end to the universe. Basically, this model refers to the basic assumption that the expansion of the universe will continue indefinitely. The further space expands, the lower the temperatures prevailing there will ultimately become. In the course of millions of years, the values will eventually approach absolute zero, with fatal consequences. First, the gas for the formation of new stars will be exhausted. The stars that already exist will continue to shine until they run out of fuel. What follows is a period of galactic darkness and cold. If the thesis proves true, that protons are not stable and decay, the last remnants of stars would also disappear. What would remain then would be black holes, which dissolve by Hawking radiation. Consequently, the temperature would reach a value consistent throughout the whole universe, where no thermodynamic work would be possible. With its gigantic expanses and its thousands and thousands of celestial bodies and structures, the universe as a whole is extremely difficult to comprehend. As is well known, we have sent many unmanned spacecraft into the realms of alien planets. At the same time, complex space telescopes direct their gaze to those secrets that hide in the remotest areas of our cosmic neighborhood. But despite all the milestones achieved in modern space exploration, we are still far from having deciphered all the mysteries of the cosmos. This is due in no small part to the fact that there may be galaxies and formations in space that simply elude our earthly gaze. But what could be hiding outside the observable universe? Have researchers already come across clues in the course of their work? Limited view to the stars. When we turn our gaze to the firmament on starry nights, we can see for ourselves the overwhelming diversity of the universe. In view of the innumerable stars that sparkle at us from high above, we realize time and again how small we are in the overall context of the overwhelming cosmos. At the same time, however, it's also true that what we can see from our earthly vantage point by no means reflects the true dimensions of the universe. In fact, our view of the stars is limited by some natural factors. Those areas of the cosmos we can see from our Earth are defined within cosmology as the observable universe, based on the assumption that the universe is isotropic and homogeneous, which means that it always presents itself to the observer in the same way, independent of his location and direction of observation. A diagram results which explains this standard model comprehensibly, so we can imagine the observable universe as a sphere whose center forms our blue home planet. The spherical range surrounding the Earth includes all those areas visible from our point of view. In principle, the borders of this sphere are fixed by the information which can have reached us since the birth of the universe. In view of the fact that the Big Bang occurred about 13.8 billion years ago, one could assume that this number also corresponds to our terrestrial observation horizon. However, this is not the case. In accordance with the Big Bang standard model, the corresponding value is actually given as 46.6 billion light-years. It's important to note that the universe is by no means a rigid construct, but that it's constantly expanding. As a result of this cosmic expansion, the light from the observation horizon has also moved further and further towards our earthly home. Expressed in other words, this means that previously covered distances were extended subsequently. To further illustrate, those formations, which appear the most distant within the observable universe for us, lay in the time in which they emitted the light we perceive today, 40 million light-years away from us. Today, however, there is a gap of 46.6 billion light-years between us and those remote objects. Also, the redshift, the cosmic background radiation, and the so-called Hubble radius indicate which cosmic regions we can detect from our Earth. The event horizon, in turn, determines the maximum distance that a structure may currently be from us, so that its light can just reach us in a theoretical limit in the infinite future. Considering this background information, we become aware that a view to the nightly firmament is always equivalent to an optical time travel. All the sparkling formations in the night sky are therefore only snapshots of how the glistening bright celestial bodies looked in the past. If something exists beyond the boundary of the observable universe that we cannot see, this means that these objects are so far away from us that the light emitted by them has not yet had enough time to reach us. The exciting question is therefore, does something exist out there that has always been hiding from our prying eyes? And if so, what could it be? Beyond the border. Well, it's obvious that these questions are anything but easy to answer. In order to get an overview of whether there is something out there that we can't see, we also have to take into account the curvature of the observable universe. For in fact, experts cannot say with absolute certainty how the cosmos is actually structured. In addition to the question of its exact shape, this also includes the problem that we do not know whether it's a finite or an infinite construct. In order to get on the trail of this great mystery, astronomers look at the geometrical curves of the universe on large scales, which can reveal conclusions about its overall shape. If our galactic home is a geometrically flat structure, then in theory, it could be infinitely large. However, if it literally curves in on itself, like the surface of a sphere, then the volume of the cosmos is finite. In fact, some recent research suggests that the universe is almost perfectly flat. Although this is by no means a finding set in stone, it would mean that the universe would have to stretch on further. In the reverse conclusion, this would also mean that beyond our observation border, more cosmos lies hidden. Some astronomers represent the assumption that the regions of the universe invisible to us can be compared with the areas known to us regarding their structure and the objects contained in it. The expression of infinity implies, however, still another conceivably exciting factor. Within infinity, simply everything would exist that can exist. Let's think just for a moment about this overwhelming thesis. Within the framework of infinity, we would also eventually come across a perfect image of our domestic solar system, including a planet Earth and our identical double. However, while such compelling conjectures cannot be proven from a scientific standpoint, in 2008, researchers stumbled upon a most unusual circumstance that could give us a premonition of what lurks beyond the observable universe. A strange observation. The great cosmic mystery that has kept experts spellbound for several years now goes by the name of Dark River. But first things first, based on the common assumptions of cosmology, the proper motions of galaxy clusters should be randomly distributed in all conceivable directions relative to the cosmic background radiation. However, NASA staff at the Goddard Space Flight Center discovered during a data analysis that this theory does not agree with real processes in the cosmos. So the researchers noticed that some galaxy clusters are literally torn in one and the same direction. Particularly surprising, the speed with which this movement takes place increases with distance ever further. So it seems as if something is hiding beyond the observable universe, which practically pulls the affected galaxy clusters. However, the cause of this strange spectacle is currently completely unknown. Even more mysterious is the fact that ever more galaxy clusters are affected by this phenomenon. At the time of the discovery, 700 clusters were involved in the Dark River, but their number has since doubled to 1,400. A thesis that tries to explain this ominous circumstance is based on the fact that the registered movements represent a relic of the influence of a no longer visible area of the cosmos before cosmic inflation. In other words, somewhere out there, massive structures or objects could be lying dormant, exerting an extreme gravitational influence. It's possible these could be accumulations of matter and energy in orders of magnitude that dwarf everything known so far. To get an impression of the corresponding dimensions, it's worth taking a look at the so-called Hercules Corona Borealis Great Wall. Whether this so-called superstructure actually exists is still hotly disputed among experts. If it does exist, however, it would possess a size of a breathtaking 10 billion light-years. Consequently, we would be dealing with the largest and most massive structure in the entire observable universe. No less exciting is the thesis that the incomparable gravitational forces come from other universes. Accordingly, our cosmos would form only a tiny link in a chain of innumerable worlds. According to the theory of chaotic inflation, the majority of the universe would expand exponentially for all time. The unbroken expansion would abate thereby only within different bubbles, where again, a multiplicity of sub-universes form. The individual sub-universes can contain again different values of the natural constants and are subject to completely individual physical laws. The new James Webb Telescope has been in operation since the summer of 2022. Since then, the largest and most expensive space telescope of all time has already caused a sensation. Even the first images showed that everything will change with the launch of the telescope. At the edge of the universe, James Webb made one startling discovery after another. The view to the edge of space. One thing is certain, James Webb looks deeper into the universe than any other telescope to date, thanks to a 21-foot mirror with 18 honeycomb-shaped segments. James Webb can capture light that has been traveling to us for more than 13 billion years. The 69 by 46-foot telescope is packed with high-tech, state-of-the-art instrumentation. According to NASA, the telescope's infrared sensors are so sensitive to infrared light that even the slight warmth of a bumblebee at the distance of the moon can be detected. As a result, this telescope will eclipse anything that has been technically possible. James Webb is considered 100 times more sensitive and powerful than the Hubble Space Telescope. The mission motto could be sharper, deeper, wider, and in doing so, the technology delivers vastly improved color imaging compared to Hubble. James Webb is not just a telescope, but something like a gigantic time machine. Our universe is said to be about 14 billion years old, and Webb can safely capture light that has been traveling to us for 13.5 billion years. Thus, this giant looks to the edge of time. Although Hubble has already been a revolutionizer in space exploration, the old telescope couldn't look quite as deep, and the images Hubble could provide of the oldest galaxies were comparatively fuzzy and blurry. Unlike Hubble, the new telescope is also located much deeper in space. Hubble, to date, is located at a distance of 342 miles. James Webb, on the other hand, is positioned a full 900,000 miles from Earth in space. That is more than 4 times as far away as the moon. For NASA and all the nations involved in building the telescope, this represents a significant risk. Hubble has had to be repaired and upgraded 5 times during its 30 years of operation. To do this, NASA Space Shuttle missions flew virtually to our cosmic front door and fixed it. James Webb is too far away to fly to. Repair missions could be a challenge to the development of modern space flight. NASA long ago discontinued its Space Shuttle program due to technical defects. The only spacecraft currently carrying humans into space are the Dragon shuttles from SpaceX and Elon Musk. Of course, if SpaceX flies humans to Mars as planned, starting in the 2030s, they could stop by James Webb and change a few light bulbs. We now look at what James Webb has shocked the world of science with. The oldest objects. Even on the first picture NASA presented to the world public, things were to be seen which should not exist at all. The deep field picture shows in reddish coloring the oldest galaxies of the universe known so far. Here, first investigations provided for an unexpected sensation because the oldest galaxies are to all appearances much older than assumed so far. Scientists must now come to terms with the fact that massive and luminous galaxies already existed 200 million years after the Big Bang. At the moment, international expert teams are examining the authenticity of these findings and looking at whether there could have been perhaps an error with the past determination of distances and the age of galaxies. If the accuracy of the measurement methods is confirmed, all theories about the Big Bang will have to be rewritten, and researchers may soon have to find new explanations for the beginning of the universe and time. At the top of the list of the probably oldest galaxies are currently the galaxy Glass Z13 with an age of 13.5 billion years, and the galaxy Sears 93316, which could be even a tad older. Remember, the Big Bang should be about 13.7 billion years ago. And after the Big Bang, there was supposedly nothing for a very long time. But Webb's pictures show something else. Are there exoplanets with life? The second sensation that NASA published was only a few days ago. On January 11, the space agency announced observational data collected as early as August 2022. Detecting exoplanets is one of the telescope's major tasks. Like no other before it, James Webb can sense tiny planets at incredible distances as they pass in front of their stars, or the telescope analyzes minute changes in the star's light spectrum to determine the presence of planets. On top of all this, the telescope is equipped with instruments that, for the first time, allow it to make the finest measurements in the vicinity of exoplanets. The determination of a planet's composition and any atmosphere can thus be examined in greater detail. The first planet analyzed in this way was LHS 475b, a rocky, Earth-sized exoplanet orbiting a red dwarf star about 41 light-years away in the constellation Octans. The planet is much closer to its star than Earth is to it, and a year lasts only 2 days on LHS 475b. By analyzing the transmission spectrum, scientists are now trying to determine what is present in the planet's atmosphere. In doing so, James Webb proved that it can easily detect a whole range of molecules. So far, the data have not been sufficiently analyzed to say for sure that LHS 475b has an atmosphere and possibly the conditions for life. But again, the first successful measurement was only the starting point, and we can look forward to more sensational results. The search for the edge of the universe. Does the universe have a beginning, an end, and boundaries? James Webb is intended to do no less than finally clarify these essential questions of mankind. In practical terms, the telescope can look back in time 13.5 billion years. That should be to shortly after the Big Bang. It remains to be seen whether James Webb's scope can look back even further than previously thought. As we've already told you, the telescope has already turned the world of science upside down with the first images of extremely old galaxies. If researchers have found evidence of the Big Bang thanks to James Webb, at least the starting point would have been confirmed. But this is not so, and also no hints were found on boundaries of the universe, which existed shortly after the Big Bang. In this context, of course, the question immediately arises whether James Webb can theoretically look to the edge of the currently existing universe. However, this question must be answered quite clearly with no. James Webb can only capture light and make sources visible. The light that hits the telescope's mirrors has been traveling in the cosmos for a different amount of time before it reached us. The image that James Webb records thanks to the light always shows the position of the light where it was at the moment it was emitted. Galaxies whose light reaches us after 13 billion years very probably do not exist today. Even the light of our nearest stellar neighbors in the Centauri system takes about 4 years to reach us. We then see the stars as they looked 4 years ago. So, since we have practically zero possibilities to look from Earth into the existing universe at the moment, we can't see to an edge either. As we know today, not only galaxies move in an expanding way through space, but the whole space expands. The starting point was supposedly the Big Bang, which is now under scrutiny, a previously unexplained factor in the overall structure of the universe, and its expansion is black or dark matter. Here too, James Webb is expected to provide new insights. However, the first measurements on this are still pending. The results could be the much-needed pieces of the puzzle of the overall cosmic picture, or once again terrify the world of science. Dark matter is very likely an essential building block of the universe. It's the original ground of a not less mysterious network which forms the basic structures of the universe. That there is dark matter is clear. It only escapes all physical rules known up to now, and it's exactly this that provides for sleepless nights for scientists. What if everything astronomers and physicists thought they knew about the cosmos is wrong? If the telescope continues to deliver results that do not fit the previous theories, we will be able to experience in the coming months and years how the history of the origin of the universe will have to be completely rewritten. What do we really know about the cosmos? What we know and know for sure at the moment is the size of the universe known so far. This is the part of the cosmos that we can observe with telescopes. However, we currently have absolutely no way of estimating how large the universe actually is. James Webb's observation radius is 13.5 billion light-years. The total size of the known cosmos is about 28.5 gigaparsecs. Parsec is a so-called astronomical unit, shortened as AE, for cosmic distance specifications. One astronomical unit corresponds to the distance between Sun and Earth, or about 90,000 million miles. One parsec corresponds to 3.6 light-years, or 5,880,000,000 miles. So 28.5 gigaparsecs would put us at about 58 billion miles, and we humans can hardly imagine that spatially. So far, researchers assume that we on Earth can only see light up to a distance of 16 billion years. Researchers call this line the event horizon. What happened before that, we humans will probably never know, unless our technologies make dramatic progress. But researchers are confident that they can reconstruct events thanks to computer simulations. Our eye in space. To understand the revolutionary insights that the use of a space telescope can provide, it's first worth taking a look at some of the milestones of Webb's predecessor, Hubble. Launched into space on April 24, 1990, Hubble provided us with images of galaxies in unprecedented detail. Away from the famous Hubble deep fields, the instrument allowed us to take an in-depth look at the acceleration of cosmic expansion. Even distant supernovae could be analyzed for the first time with the help of the Space Telescope. Last but not least, Hubble provided evidence that the centers of nearly all galaxies are graced by supermassive black holes. However, if we now compare the performance of the Space Telescope with the potential of Webb, it becomes clear to us that the joint construction by NASA and ESA only exposed the tiny tip of the cosmic iceberg. In fact, Webb is up to 100 times more sensitive to electromagnetic waves than its predecessor. Specially designed for infrared astronomy, the instrument, which weighs over 6 tons, is able to let its technical eye wander from the red part of visible light to the mid-infrared spectrum. Why this is so important for deciphering the universe becomes clear when we recall the cosmological redshift. In simple terms, light originating from distant and thus early regions of the cosmos is shifted into that very infrared region. This light has the characteristic property of passing through interstellar gas clouds much better than visible light. Equipped with its special capabilities, Webb is thus expected to target the first luminous objects and galaxies born in the first millennia after the Big Bang. To illustrate Webb's often cited capabilities with a comprehensible example, NASA points to the following. From Earth, the Space Telescope would be able to register the heat of a bumblebee on the surface of the Moon. But what is the technical background behind these amazing capabilities? First and foremost, there is the massive primary mirror. Composed of 18 individual, perfectly matched segments, the mirror has a diameter of 21 feet. The individual components are coated with an extremely thin layer of gold. The reason for this is that gold reflects infrared light significantly better than other metals. For Webb to work properly, it must be kept cool at all times. This in turn is accomplished by the 5-layer sun shield, which when folded out makes it the size of a tennis court. The equipment is permanently cooled down to -369 degrees Fahrenheit. This ensures that the telescope's sensitive instruments are protected from incident solar radiation. If major complications do arise, fingers are crossed. Webb's target orbit around the Lagrange point L2 is about 1 million miles from Earth. As a result of this great distance, no manned repair missions can be completed. So now that we've had a brief look at the technical makeup of the Space Telescope, let's turn our attention to another exciting question. What will Webb get to see as part of its science mission? The observable universe. As mentioned earlier, Webb will analyze the first luminous formations of the cosmos in the coming years. Given the telescope's deep look into the vast expanse of space, an intriguing question arises. Will Webb be able to observe the edge of the universe? And does such a thing even exist? According to our current state of knowledge, we don't know how big the universe is. Due to the gigantic dimensions of the cosmos, we cannot see its edge, if it exists at all. Also, the question about the form of the universe remains unanswered. That area we can see from our point of view is appropriately called the observable universe. Assuming that the cosmos is isotropic and homogeneous, or in other words, that it always presents itself to the observer in the same way, independent of his location and direction of observation, this results in a spherical observation area around the Earth. However, the distance up to the observation horizon is now thought to be more than 13.8 billion light-years. It's true that the Big Bang happened approximately 13.8 billion years ago. However, we must also consider the constant expansion of the cosmos. Since distances already covered have subsequently become longer, the distance to that optical barrier is therefore 46.6 billion light-years. The most distant objects in the firmament were, at the time they emitted that light, only 40 million light-years away from our blue home planet. However, since these entities have long since crossed the event horizon, it's impossible to say anything about their current processes. The event horizon indicates how far an object may be away from us at present, so that its light can still just reach us in the infinite future. As a result of these natural constraints, structures exist in the universe that we will never see. The edge of the observation horizon. Among the most distant and thus oldest galaxies tracked down so far is GN-Z11 in the constellation of the Big Dipper, about 13.8 billion years old. This gravitationally bound cluster is only 4% the size of our home galaxy, with its star count corresponding to only 1% of the Milky Way. First discovered in 2016, GN-Z11 has since earned the title of the oldest known galaxy and the most distant known structure in the cosmos. As a result of the expansion of the universe, the distance between GN-Z11 and Earth is about 32 billion light-years. And this is where the future use of the James Webb Space Telescope comes into play. Once again, as a reminder, the technical equipment can operate in the mid-infrared spectrum, and basically, the closer an object is to the observation horizon, the more redshifted the radiation we can observe from it. Or in other words, the closer it is to the edge of the observable universe. For those entities that are directly on the observing horizon, the redshift is actually infinite. The popularly cited assumption that such objects move away from us with the speed of light, however, is wrong, because actually they drift away from us with more than threefold the speed of light. But how is this possible at all? Doesn't such a speed contradict Einstein's theory of relativity? The answer is no. To understand this, we have to consider the characteristics of cosmic expansion. Because in fact, it's not a movement in space. Rather, space itself is expanding. Beyond the observable universe. Given our limited view of the stars, a central question arises. What lies beyond the observable universe? The sobering answer is, even the James Webb Telescope will not be able to decipher this great mystery. Scientists can only conjecture concerning this exciting topic. One theory says that the regions of the cosmos invisible for us are built approximately the same as those areas we can see. As is well known, it's often assumed that the universe is an infinite structure. But what does the oft-quoted concept of infinity actually mean in reality? Well, it can be summarized as follows. Infinity contains everything that can exist. If one follows this principle, then somewhere out there for each of us a perfect double would exist. However, while we can only enter the world of speculation in this regard, the ominous dark flow could provide us with a real clue to those structures that lie dormant beyond the horizon of observation. But what is this mysterious dark flow all about? NASA's WMAP spacecraft investigated the irregularities of the cosmic background radiation between 2001 and 2010. This almost isotropic radiation in the microwave range is a relic of the Big Bang and fills the entire universe. If one follows the common assumptions of cosmology, the proper motions of galaxy clusters relative to cosmic background radiation should be randomly distributed in all directions. The scientists were all the more surprised when they discovered that many galaxy clusters are literally pulled in one and the same direction. But that's not all. The speed of this inexplicable flow even increases with distance. Consequently, it seems that beyond the observable universe, there is a huge structure that literally pulls the galaxy clusters into its spell. In the meantime, 1,400 galaxy clusters have been identified as participating in this dark river. Some experts believe that it's the effect of a neighboring universe, or else the effects of a space-time region that is drastically different from the observable universe. Even if the exact background of the dark flow has not yet been deciphered, the exciting discovery, nevertheless, provides us with an important insight, namely, that we are still far from having completely unraveled the cosmos. The nightly view of the starry sky is simply overwhelming. While all the countless objects and structures in the firmament sparkle at us, there is one thing we should not forget. What we can survey of the universe reflects just a vanishingly small fraction of the totality of the cosmos. Despite all astronomical milestones, we are still not able to describe the exact shape and extent of the universe. All the more frightening, the observation researchers made some time ago at the edge of the observable universe. To all appearances, a gigantic something slumbers outside of our field of vision, which possesses an enormous influence on the structures of space. But which entity could possess the power to irretrievably cast its spell over countless clusters of galaxies? Limited research view. As already described at the beginning, the universe as an overall construct has always embodied the great unknown. The fact that the knowledge of the researchers in this respect still shows enormous gaps is to be attributed above all to the fact that our view to the stars carries blinders due to some natural factors. By nature, it is not possible for us to see the entire cosmos. That part of the universe that we can see from our earthly vantage point is appropriately called the observable universe, assuming that the cosmos is isotropic and homogeneous. That is, it always presents itself to the observer in the same way, regardless of his location and direction of observation. This results in a spherical area around the Earth that reflects our observation space. Thereby, every arbitrary place in space possesses an individual observable universe, which can overlap with those of others. That view boundary, that includes all information that could have reached the Earth since the Big Bang, is called the observation horizon. Against the background that the hour of birth of the cosmos occurred about 13.8 billion years ago, one could think, therefore, that the distance up to the observation horizon is also 13.8 billion light-years. But this is not the case. Instead, the corresponding value is given with 46.6 billion light-years, because in fact, we must not forget that the universe is by no means a rigid, unchanging structure, but one which is constantly expanding. However, the universe does not enlarge itself into an existing space. It is rather the space itself which expands incessantly. Thus, those structures, which are today at the border of the observation horizon, were in the time when they radiated their light just 40 million light-years far away from our terrestrial home. In other words, this means distances that have already been traveled have been subsequently extended. However, the exploration of such remote areas always resembles a cosmic time travel. Since the corresponding objects have long since passed the event horizon, we cannot make any statements about those processes that are currently occurring there. Dark flow. Although the question of what lies beyond our observable universe may remain unanswered forever, a few years ago, experts made a discovery that could give us a disturbing foretaste of the great unknown. Back then, in 2008, it all started with the analysis of cosmic background radiation. As a brief reminder, this is a nearly isotropic radiation in the microwave range that fills the entire cosmos and embodies a relic from the primordial age of the universe. Within the physical cosmology, the background radiation plays an outstanding role and is listed so as incontestable proof for the Big Bang Theory. To measure the variations in the cosmic background radiation, NASA's WMAP spacecraft was deployed between the years 2001 and 2010. At its core, the background radiation changes due to the motion of clusters of galaxies, from which its pace and direction can be inferred. When a NASA team led by Alexander Kashlinsky analyzed the WMAP data, which had been collected over a period of 3 years, an unexpected phenomenon was revealed. According to the data, the galaxy clusters studied exhibited an amazingly coherent motion, with the flow velocity increasing with increasing distance. Or in other words, the gravitationally bound clusters of thousands of galaxies fell into the grip of an immense gravitational pull. The daunting problem scientists face in investigating this is the fact that we are still completely in the dark as to the cause. A renewed data analysis that took place 2 years later showed that the number of participants of this ominous dark flow had even doubled, while 700 galaxy clusters had previously been affected by the unusual flow pattern. This time, the researchers counted 1,400. But what could cause these massive structures to align along a common axis and drift away? The unrevealing answer to that question is, we have no idea. In this regard, Alexander Kashlinsky stated that we are dealing here with an undefined influence that has already left our observable universe. Especially exciting is the explanation that locates the background of this observation in the existence of a neighboring universe. Alternatively, there is a thesis that beyond the observation horizon space-time region, something slumbers. At this point, we should mention, however, that Kashlinsky's remarks are not only well received in the ranks of his expert colleagues. Although other investigations have not delivered any clues for the postulated dark flow, the main author of the study defends his results vehemently. In this regard, he can be quoted as saying, "At this point, we don't have enough information to see what it is or to narrow it down. All we can say with certainty is that the world far away is completely different from what we can see locally. Whether it's a neighboring universe or a different space-time structure, we don't know." Beyond the boundary. Let's take Kashlinsky's mind game to the mat in order to devote ourselves to a conceivably exciting question. What entities are hiding outside the observable universe? A basic message in advance. As a result of the limiting factors that we presented to you at the beginning, researchers can only speculate in this respect. The least exciting explanation is based on the assumption that those areas beyond our optical limit present themselves with respect to their structure and the objects contained therein in approximately the same way as the structures visible to us. However, the matter becomes much more spectacular if we take up the neighboring universe mentioned by Kashlinsky. Centuries ago, philosophers of antiquity dealt with the question of parallel worlds. While these were often mystical realms of gods or devilish underworlds, modern researchers do not shy away from this exciting field either. With the help of the many worlds interpretation of quantum physics, it could be explained why the probability of each measured value in a quantum physical system can be precisely calculated, while the actual measurement results cannot be predicted. Consequently, it is conceivable that our cosmos does not comprise the big whole at all, but embodies only a tiny link in an infinite chain of other universes. To explain the background of such a multiverse, the Russian cosmologist Andrei Dmitrievich Lind put forward the theory of chaotic inflation. According to this thesis, the majority of the cosmos continues to expand eternally in an inflationary manner, with this process only coming to a halt in a few partial bubbles. Within these bubbles, again a multiplicity of sub-universes form. However, not all universes are the same. Accordingly, each cosmic world could contain different values of the natural constants and thus also completely independent physical laws. That the individual sub-universes are teeming with life is therefore considered improbable. Thus, the appropriate values of the natural constants would be able to pave the way for the development of life in few universes. Open questions. Whether and when the question about the existence of parallel worlds will be solved stands at present still proverbially in the stars. But no matter whether our universe is a tiny partial bubble or embodies the cosmic whole, that our universe is still overshadowed by gigantic question marks is beyond question. This already starts with the often used phrase of the infinite universe, which despite its frequent use is by no means proven. Meanwhile, the same is true for the shape and volume of our cosmic home. At the first moment, one would assume that the shape of the universe resembles a sphere, but this is only one of many assumptions. Whether we will one day unravel this fundamental mystery, however, the future must show. Our current astronomical observation data do not allow us to determine the shape of the cosmos. We remain curious about what realizations researchers will make in this regard one day. And now it's your turn. What do you think about the mysterious observation that the experts recorded at the edge of the observable universe? Do you have any ideas about the structure of the countless clusters of galaxies? As always, drop us your thoughts, suggestions, and feedback on our video in the comments below. Want to learn more about the most unusual discoveries in space? Then take a look at the other contributions of our channel, which we have linked here in the credits for you. Thanks for your interest, take care, and we'll see you next time.